Okay, let's work this first one. So, besides what we already mentioned, I put step 1 to look again at the fact that x2 is greater than or equal to 2 and x3 is strictly greater than 2, which we mentioned is the same thing as x3 being greater than or equal to 3 since we're talking integers. So what that means is that we have to pre-allocate those variables, and we really only have 11 minus 2 minus 3 equals 6 in our total. That can still be distributed among the 4 variables. Think about it with donuts, for instance. If you have to have at least 2 of type 2 and at least 3 of type 3, then you go ahead and get that out of the way, put those in your bag, and then you still need to buy 6 more donuts to fill up the bag. So whenever you have lower limits, then you just restate the problem, and now we'll use 6 instead of 11 all throughout. The second step to notice is that the upper limits are each rules that cannot be broken. Now, I'd already mentioned before that x4 less than or equal to 11 isn't really a rule because the total is 11, so it just means that x4 can be anything up to the total. So we only have 3 rules really, and we pictured them here. We have to keep in mind the lower limits, x2 greater than or equal to 2 and x3 greater than or equal to 3. So in the picture on the right, I drew them as bookshelves, x1, x2, x3, and x4. I put the 2 in x2 and the 3 in x3 already. Those are pre-allocated. Then there's 6 remaining in the total to allocate, and the question mark means I can put any amount in those 4 variables out of that total to 6. But then to keep track of the rules say that x1 can't be greater than or equal to 5. So 5 dots there. That would break that rule. Then x2 can't be greater than or equal to 4. So I put in 2 dots because 2 dots plus the 2 pre-allocated spots would be 4, which would break the rule. And then x3 can't be greater than or equal to 8. So there's already 3 pre-allocated, and so I put 5 more dots to show what would break the rule. So, and then I wrote it down here on the left as well. And this is the answer to the problem, starting out answering it. So first off, we have to put in the total number of ways. After pre-allocating, there's a total of 6 plus 4 minus 1, choose 4 minus 1. Ways to fill in those question marks. Then breaking one rule at a time. Need to subtract off the cases for breaking each of those rules. So the first one would be x1 greater than or equal to 5. That would break the rule. So I subtract off the 5 as if I put 5 in x1. And that means there's 1 left to allocate anywhere. So I'm left with 1 plus 4 minus 1, choose 4 minus 1. Then for variable x2, I want to break that rule and put 4 in x2. Now that really just means putting 2 more because I've already got 2 there. So then what I'll be left with is 6 minus 2, or 4, and then plus 4 minus 1, choose 4 minus 1. So you'll notice the only thing that's changing is that first number. I just have to figure out, if I'm going to break a rule, how many I have left to allocate. Alright, so then the last one, x3 greater than or equal to 8, would be breaking that rule. So I see that if I put 5 more in x3, that gets me up to the 8. So then there's 6 minus 5, or 1, plus 4 minus 1, choose 4 minus 1 there. Then I think about breaking 2 rules at a time. Now, as you can see already, I'm not going to get anything else, but let me explain why. So breaking two rules at a time would be adding back in the intersections. So the first one would be if I broke the rule that x1 is greater than or equal to 5 and x2 is greater than or equal to 4, then I would add back in the intersection of those. But is there any way to do that? If x1 is greater than or equal to 5, so I put in 5 in the x1, and x2 is greater than or equal to 4, I put in 2 more in x2, then I've used up 7, 5 plus 2. And that's more than 6, so there's no way to do it. And in fact, you could put in those numbers. You would say start with the 6 that I need to allocate, and subtract the 5 and the 4. So I would subtract, subtract the 5 and the extra 2. So subtract the 7, I get a -1, and then plus the 4 minus 1, choose 4 minus 1. Will give me something that makes no sense. It will give me 2, choose 3, so a 0. So if you notice that these are impossible, you can just put down the 0. And if you don't notice and you see that you're getting a small number choosing a larger number, then you realize that it is 0. Same for x1 greater than or equal to 5 and x3 greater than or equal to 8. No way to do that with 6 to allocate. And same for the rest. The last one is when I would try to break all 3 rules, and that would be another subtraction. So, but again, no way to break all 3 rules. No way to even break just 2 of them. So then the final answer is that 9 choose 3, just adding together all the additions and subtractions, and it came out to 41 total.